In this video lecture, we look at an example where it's easier to compute the area between our two curves by setting up an integral with respect to y. So let's consider the region enclosed by 4x plus y squared equals 12 and x equals y. And we're going to compare what the area setups look like for an integral with respect to x and an integral with respect to y. So first let's shade the region that we're looking at, and then we're also going to need to find the intersection points between these two curves. So let's see, when x is equal to y, I can replace this x here with y and find my y coordinate where these two curves intersect. So I have 4y plus y squared equals 12. So this is y squared plus 4y minus 12 is equal to 0. So if I factor this, I have y minus 2 and y plus 6. That should give me my positive 4y for the middle term and negative 12 for the constant term. So I see that y equals 2 and y equals negative 6 are the y coordinates where my curves would intersect. So it must be that this point down here is negative 6 and this point here is 2. Since this is the curve y equals x, this point here would be x equals negative 6, so I just want to know what this point is to get the farmost x value of my region. I notice that I have this blue curve here is my parabola. This looks like the vertex is occurring where the y coordinate is 0. So I see if I plug in y equals 0 into this, then x would be 3. Okay, so if I want to set up an integral with respect to x, I would need not only my curve here y equals x, but I'm going to need to get this parabola as a function of x. So notice that we have 4x plus y squared equals 12, so this means that y squared is equal to 12 minus 4x, or that y is equal to plus or minus the square root of 12 minus 4x. So that actually means that this sideways parabola here is two different functions of x put together. So if I make this top part here a little bit darker, this darker part here is my positive square root. That's y equals the square root of 12 minus 4x. And this lighter blue part is the curve y equals negative the square root of 12 minus 4x. We see that all of the y values for this part of the curve would be negative. So now I have to think about maybe setting up my area integral with respect to x. So I can think about, slicing this up into different pieces here. I notice that all the way until this location here, this red curve would be the top curve, and this lighter blue curve here would be the bottom curve. But then when I get into what's happening here after, looks like this will be x equals 2, I would have this dark blue curve here as my top curve and this lighter blue curve as my bottom curve. So I'll have to look at this as a sum of two different integrals. So I'd have an integral from negative 6 to 2, where my top curve here would be x and the bottom curve here would be negative the square root of 12 minus 4x. Or I have plus that dx. Then I'd have plus an integral from 2 to 3, where my top curve here would be my positive square root of 12 minus 4x, and the bottom curve here would be this negative square root of square root of 12 minus 4x, or I'd have plus that positive there. So that looks like rather a messy setup, but that would represent my area of that region with respect to x. So what about looking at the area of this region with respect to y? So maybe I'll draw a second version of my curve here. So I have my parabola is looking like this, and we have this line here. So we're looking at this curve. If I'm going to try to find the area of this region with respect to y instead of with respect to x, instead of doing all these vertical slices like we were before, I'll look at doing some horizontal slices, so that I'll be slicing up my interval along the y-axis into little rectangles of width delta y, and then I'll be looking at how long one of those rectangles is. So it'll be a curve in terms of y, this right curve, minus my curve in terms of y along the left. So I have x equals y for this line. I can look at it in that way. I also have 4x plus y squared equals 12, so I'd like to solve this for x in terms of y. So I see that 4x is equal to 12 minus y squared, or that x, if I divide both sides by 4 here, is equal to 3 minus y squared over 4. So that's the equation of my parabola here in terms of y. And I have these nice y bounds from -6 all the way up to, let's see, 2 for my region. So if I'm looking at an integral here with respect to y, I can have an integral from -6 to 2. Okay, now I've got this width that's equal to delta y, and the height of my rectangle equal to this right curve of 3 minus y squared over 4 minus the left curve of y. So we have 3 minus y squared over 4 minus y dy. And looking at this setup versus the setup we had in part A, certainly the second one looks like it's going to be a little easier for us to actually integrate, because we just have to integrate these powers of y instead of having to integrate these square root functions. So when I do have a function that is defined in terms of y, it can be easier for me to compute the area by looking at an integral with respect to y, slicing it horizontally, instead of an integral with respect to x where I looked at vertical slices. So I see that I would take the antiderivative of each of these different pieces here. I'd have 3y minus y cubed over 12 minus y squared over 2, evaluated from -6 to 2. So we would have 6 minus, let's see, 2 cubed over 12, 8 over 12, minus 2 squared over 2, so that'll be -2, minus -18, minus -6 cubed over 12, minus 36 over 2. And these are a little bit larger numbers, but with a little bit of arithmetic here, we can find that our area will end up being 64/3. And we would get the same thing by evaluating our setup here in part A, and you can verify that, but we would prefer to do the work of computing the integral with respect to y, since that's going to be a little bit easier. Please let me know if you have any questions on this material.